Humans have long dreamed about what life might be like on distant planets. That question can now be answered thanks to the James Webb Space Telescope, the most potent telescope currently in use. Scientists have observed some oddities from one of the planets in the system, Proxima b, while studying Proxima Centauri, the nearest star system to Earth, which is only 4 light-years away. The brightest minds in science have been baffled by these abnormalities, which are known as artificial lights. However, what are they? Do these lights imply that there is sentient life on Earth? Come along as we examine James Webb's life-altering, horrific discovery of city lights. As of the now, we only know about life on Earth. The topic of whether life exists elsewhere in the universe has been raised since the dawn of humanity. The search for extraterrestrial intelligence, SETI, project was started in 1984 by American astronomers Jill Tarter and Thomas Pearson to conduct such an interstellar search. The nonprofit's goal is to collect radio transmissions from space. Because radio waves are less absorbed or scattered than other forms of radiation, they can travel farther and are therefore more likely to be picked up by the 42 radio telescopes that comprise the unique Allen Telescope Array in the Californian Cascade Mountains. But no substantiated alien signal has been found in the last 30 years. Following that, the successful launch of the James Webb Space Telescope facilitated the investigation of a variety of far-off, unexplored planets orbiting faraway stars. It will make use of the world's largest telescope, which is equipped with extremely sensitive detectors and is floating around 1 million miles from Earth. More than 4,000 planets, also known as exoplanets, have been found orbiting other stars since the discovery of the first planets outside of our solar system 20 years ago. NASA estimates that there could be trillions of exoplanets in the cosmos. Extraterrestrial plant life may include the first indications of life outside of our solar system. On its way to Jupiter, the Galileo spacecraft discovered a clear sign of plant life and turned its instruments back toward Earth. The vegetation red edge (VBI) signature, a combination of red and infrared lights reflected by plants, was picked up by the device. For example, a jungle-covered planet like Earth ought to have a powerful and noticeable VBI signal. The VBI of distant Earth-like planets in the habitable zone around stars will be measured by the JWST. These measurements may be crucial indicators of life in the atmosphere of exoplanets. The JWST might be able to pick up sunlight as it enters a planet's atmosphere after passing over its star. Spectroscopy would then be used to find the missing wavelengths. The atmosphere's atoms and molecules absorb particular wavelengths, forming a distinctive fingerprint that the JWST can identify. The composition of the atmosphere and the potential locations for life can be ascertained using this technique. Life might probably live on worlds that resemble Earth and have atmospheres that are comparable to ours, with a preponderance of carbon dioxide, nitrogen, and oxygen. One might be able to identify technological life by searching for components that aren't often present. Aliens keeping a close eye on Earth's atmosphere would likely notice the presence of chlorofluorocarbons, CFCs, which are produced for use in cleaning and refrigeration products. A definite sign of civilization would be CFCs detected in planetary atmospheres by the JWST. It's possible that life on exoplanets differs greatly from life on Earth. Even life on Earth, such as extremophile organisms, might appear strange at times. This category of creatures, mostly bacteria, can survive in conditions that would kill other living things. Some may tolerate temperatures as low as 4 degrees Fahrenheit, while others can tolerate temperatures as high as 250 degrees Fahrenheit. On Earth, some of them can be discovered in regions where we wouldn't expect to find any life at all, while others can thrive in strong acids with pH values below 3. However, it could be wise to begin with worlds like Earth first because they are more likely to host life than planets with extreme temperatures or acidic environments. Prime candidates might orbit a stable star and have temperatures high enough to support liquid water on their surfaces. Our Sun is classified as a yellow G-type star. In our cosmos, these stars are less frequent and usually have shorter lives. Since red dwarf stars are more common and have lower temperatures and luminosities than the Sun, there is a greater chance that planets orbiting these stars will be studied. Because these stars have far longer lifespans, there is more time for life to form and for evolution to produce complex life forms. JWST's first mission will focus on the TRAPPIST-1 planetary system, located around 40 light-years from Earth. 7 rocky planets the size of Earth orbit a serene red dwarf star. There may be liquid water on the surface of 3 of the rocky planets in the so-called habitable zone. Because of the close orbit of its planets, TRAPPIST-1 emits light that is comparable to Earth's, despite having a considerably smaller and cooler mass than our Sun. Proxima Centauri, our nearest star and a red dwarf star 4.25 light-years from the Sun, is the best place for humans to glimpse city lights outside of the solar system. A planet needs to be 20 times closer to Proxima than Earth is to the Sun in order to sustain life based on liquid water, since Proxima is roughly 600 times fainter than the Sun. In a Goldilocks-like habitable zone where the light intensity is just right to melt water, scientists found a planet with 1/3 the mass in August 2016. Proxima Centauri is circled by Proxima b. Because Proxima b orbits its red dwarf star, Proxima Centauri, only 46 million miles away, it may be an airless, lifeless planet. The Earth is 93 million kilometers away from the Sun. Because of its near orbit, the planet Proxima b is vulnerable to powerful solar winds that have the potential to totally obliterate its atmosphere. It does, however, also receive enough sunshine to support Earth-like temperatures and liquid water. Proxima b is believed to be tidally locked, meaning that it always displays the same side to the star as the Moon does with respect to Earth due to its close proximity to the star. About 18% of the mass of the Sun, Proxima Centauri burns far less brightly than one might expect for a planet that is only 5% of the Earth's distance from the Sun. It should be a red-hot cinder, but since Proxima b receives just 65% of Earth's radiation from the Sun, liquid water might readily live there as long as the planet has an atmosphere to retain heat. The planet is not particularly conducive to life, though. Since it always faces the same way toward the star, it is most likely tidally locked, creating permanent day and night sides with notable temperature variations. Because of its closeness to Proxima Centauri, the planet also receives 100 times as much high-energy radiation as Earth, including ultraviolet and X-ray light. During star flare-ups, high-energy particles are also hurled at Proxima b. The planet might be in danger unless it possesses a shielding magnetic field like Earth's. Nonetheless, there are several practical circumstances that might make it a nice world. Unfortunately, models indicate that the freezing off of volatile gases on the night side may make the atmosphere of tidally locked planets vulnerable to a quick collapse. Volcanic activity can restore our planet's atmosphere, and it is less likely to escape from worlds with powerful magnetic fields. We cannot even speculate as to whether Proxima b has an atmosphere because we have no information about the strength of its magnetic field or volcanic activity. However, we are eager to find out if Proxima b has a highly developed civilization because an atmosphere requires the presence of seas, and the two combined require the presence of life. The night side, which would otherwise be too chilly and dark for suitable habitation, might be lit and warmed by energy produced by solar panels covering the day side. There is a race to see if Proxima b crosses the face of its star as viewed from Earth since its discovery. By determining the planet's mass and size through these transits, scientists would be able to compute its density. Finding the density would confirm that the planet is made of rocks and reveal what kind of materials were employed to manufacture those rocks. Starlight may travel through the planet's atmosphere during a transit, revealing its nature. But there is just a 1.5% chance that the orbit will line up properly for scientists to see a transit. The situation is further complicated by the star's tendency to flare. The star is challenging because a rocky planet absorbs sunlight and emits it as infrared radiation due to star heat, according to Columbia University astronomer David Kipping. But stars like Proxima Centauri emit a unique kind of infrared radiation from rocky worlds. Furthermore, the James Webb Space Telescope was developed especially for the purpose of researching infrared light. The key to determining the atmosphere of Proxima b is its infrared heat signature. Moreover, there is a significant, potentially permanent attraction for Hubble's successor in the infrared part of the spectrum. Even if the city lights on Proxima b's night side were as dim as those currently used by our civilization on Earth's night side, the James Webb Space Telescope would be able to see them. If artificial illumination was focused on a frequency range 1,000 times narrower than the starlight, Webb could detect it. Because Proxima b's day side is extensively covered in solar panels, light can reflect off of its distinctive spectral borders. As an expert, Day and night are the same on Shima B, which circles around its star. Cold evening lows come after daytime highs. However, whether or not the planet is made entirely of bare rock determines how much the temperature changes from day to night. Heat is conducted by both the water and the atmosphere. In other words, Proxima B's dayside and nightside temperatures will differ more in the absence of an atmosphere. We can actually determine the exact amount of black body radiation that should be present, since the dayside will radiate all of the energy it receives from Proxima Centauri as a black body. In contrast, the night side will appear to be a frozen version of hell. We can assume the existence of an atmosphere if the day-night temperature differential is less noticeable. The JWST will conveniently complete its circle around Proxima B in just 112 Earth days, allowing it to measure the radiation from both faces of the star. The next stage will be to examine the composition of Proxima B's atmosphere, if it exists. Particularly, the presence of gases like oxygen, water vapor, and methane may be a sign that there are livable conditions, if not real live beings. But to do this, we have to collect starlight, a very challenging task, as it bounces off or passes through the planet's atmosphere. However, Webb was not designed to search for alien life, so it can only study in detail a handful of the nearest potentially habitable worlds. Furthermore, it can only monitor variations in the levels of carbon dioxide, water vapor, and methane in the atmosphere. Even if some combinations of these gases may be suggestive of life, Webb cannot detect the presence of unbonded oxygen, the strongest indicator of life. The extremely large telescope is one of the planned ground-based observatories that will be able to do a comprehensive atmospheric examination. It is expected to start operations in the mid-2020s. One of the compounds that the JWST may be able to detect is ozone. The JWST may yield data that we can think about 10 years from now till those telescopes are in service. Modern methods may be used by even more potent space telescopes to reveal starlight reflected back from a planet and hide the dazzling brightness of the planet's home star. To enhance your vision of far-off objects, try blocking the lights with your palm or anything similar. Large external umbrella-shaped satellites or tiny interior masks could be used by future space telescopes to accomplish this. It is significantly simpler to observe light bouncing off a planet once starlight has been blocked. Unfortunately, non-biological causes can also produce most of the gases released by terrestrial life. Both cows and volcanoes emit methane, and sunlight also produces this gas by photosynthesizing water molecules into oxygen and hydrogen. Astronomers will undoubtedly encounter some false positives when looking for extraterrestrial life. To determine whether a planet of interest geologic or atmospheric processes might resemble a biosignature and assist in ruling out false positives, astronomers need to have a comprehensive understanding of the planet. The persuasive evidence needed to prove the existence of life may come from the upcoming wave of exoplanet research. Preliminary data from the James Webb Space Telescope provides us with a sneak peek at the big changes ahead. One of the most important problems facing science is whether life exists elsewhere in the universe. There are two probable explanations for this. Either we are isolated on a single planet in outer space, or life is widespread throughout the universe. In either case, the final solution will probably require substantial philosophical and psychological changes on the part of individuals. We appreciate you viewing another Space Theory episode. For more incredible space-related videos, click the video on your screen while you're still here.